Hi everybody, and welcome to example 3 on page 62. Let's take a minute to read this example together. So let V and W be three-dimensional vector spaces over R. We'd like to show that V and W are isomorphic. Okay, so we're trying to show that whatever V and W look like, given the fact that they're both three-dimensional, they have to be isomorphic. So let's start by asking ourselves, what does it mean to say that the vector spaces are three-dimensional? That's really telling us about how big the basis of a basis for those two vector spaces will be. So we can pick bases for V and W that both have three vectors. Let's start by doing that. Okay, so let beta equal V1, V2, and V3. Okay, and gamma be W1, W2, and W3. We'll let those be bases for V and W respectively. Okay, and then what we're going to do is to refer back to Theorem 2.6, which allows us to define a linear transformation that goes from V to W in kind of a nice way, okay, that kind of pairs up these basis vectors that we have. Okay, so let's say it this way. By Theorem 2.6, there exists a linear transformation T going from V to W such that T of V1 equals W1, T of V2 equals W2, and T of V3 equals W3. Okay, we can kind of draw a diagram just to illustrate this. Okay, so imagine that this is our vector space V. Over here is our vector space W. Let me make this circle a little bit bigger over here. All right. And in V, somewhere in V are the three vectors in our basis beta. Okay, so maybe they look like this: V1, V2, and V3. And over here in W, okay, we've got our three basis vectors that are in gamma, W1, W2, and W3. And our mapping T just kind of pairs those vectors up with each other. Okay, now maybe one comment on this diagram that we drew. It might lead you to believe that V and W are finite sets, that both have three vectors in them. Remember, that's not the case. V and W are infinite vector spaces. We're just emphasizing the vectors that happen to form basis for V and W. Okay, and now here comes the critical observation. Okay, I claim that the rank of T and the dimension of V are both equal to 3. Okay, let's think about that. So the dimension of V is equal to 3. That's just because we know that the three vectors V1, V2, and V3 form a basis for V. Okay, so we get a dimension of 3. And the rank of T, that's the dimension of the range of T, and the vectors W1, W2, and W3 form a basis for the range of T. Okay, so we get the same number of 3. And because that's a true statement, it now follows, if we look back at one of our facts, okay, from inverse fact 5 on page 61, that T is invertible. You can look back at that fact and confirm that. Okay, and notice that what we've demonstrated is that T has two important properties. It's invertible and it's linear. And we talked about how if you put those two properties together, what you have is an isomorphism. Okay, so since T is linear and invertible, T is an isomorphism. Okay, in other words, V and W are isomorphic. All right, so the theorem that comes right after this kind of generalizes this observation. So all that we needed for these vector spaces to be isomorphic was for their dimensions to be the same. There's nothing special about the number 3. We could have chosen any finite number and kind of constructed the same argument that we did here. Okay, so going down to theorem 2.19 here, let's read this together. Let V and W be finite dimensional vector spaces over the same field. Then V is isomorphic to W if and only if the dimensions are the same. Okay, and just to maybe say a word about the significance of this result. Saying that V and W are isomorphic is really saying that the two vector spaces have identical properties. Okay, so even though V and W might contain different objects, maybe one of them contains ordered pairs and the other contains matrices, or one contains functions and the other contains polynomials, being isomorphic means that they're essentially the same vector space. There's a direct correspondence. So this is kind of an amazing theorem. It says that all that needs to be true is that the dimensions of two vector spaces are the same, and they're essentially the same vector space, if that fact is true. Okay, and in some of our future videos, we'll explore that a little bit more deeply.